Hi y'all and welcome back. So in the last video we left you with how ionic and covalent bonds are formed. Today we're going to talk more about what properties arises when each one of these bonds are formed. And first we're going to talk about electrons. So we're going to keep a tally here with each one of these properties. So the first ones are electrons. A common example of an ionic compound is sodium chloride, also known as table salt, and it's composed of, not surprisingly, sodium and chloride. So if you see sodium here in the periodic table, so sodium is around here and chloride is around here. So it's worth noting that sodium is the metallic part and chloride is the non-metallic part. Sodium has an electron here in its valence shell. So sodium wants to lose an electron. So when sodium encounters a chloride, it's just going to transfer an electron and it's going to become positive. So here we have sodium positive and chloride become negative. So when these two compounds get together, one electron is going to be transferred, forming then an ionic compound. And opposite charges, attract each other. So it's going to be an electrostatic interaction between these two, anion and cation. Covalent bonds, on the other hand, they like to share a little bit. So an example of a covalent bond is water. So water is formed by O, H, and H. So when those elements come together, each one of these elements contributes one electron. So here we have one electron from hydrogen, one electron from oxygen. They come together, and same thing from this other side of the molecule. And this type of bond is represented here as a line. And here we have, water molecule with two hydrogens and one oxygen. But in this type of molecules, electrons not necessarily get shared evenly. And this will all depend on the electronegativity, which is affected by how big the atom is. So the bigger the atom is, the less electronegative it will be. For example, here in the periodic table, here we have francium that is further away in the periodic table, so that's pretty big. So the smaller the atom is, the more electronegative it will be. And the more electrons it has close to its nucleus, the more electronegative it will be. So for example, here, fluoro will be pretty electronegative. So we see here that oxygen is pretty close to that oxygen, or oxygen is pretty close to that fluor. So oxygen is going to be pretty electronegative, and it's going to hoard a little bit of those electrons, right? So it's going to be here partially negative. And that was going to leave the hydrogens a little bit exposed, kind of like naked. So that will be, it's going to leave them a little bit more partially positive. We're going to go back here to the tally and list electronegativity. Perfect. So going back to the ionic bonds, these bonds are pretty strong and they usually form a pretty tight network on the small scale. Which, can you guess how that will look in the macro scale? I'm going to give you a couple hints so you can, try to guess what it is. So going back to the ionic bond. So here we're going to keep the example of the sodium chloride. These are usually pretty strong because they have opposite charges attracting to each other. And this is going to form a pretty tight network known as a crystal lattice. So we're going to bring over our crystal lattice. So when they're packed in that tight network, is going to look like so. So it's an intercalation of positive and negative charges. So we have here the positive sodium and the negative chloride. And they're intercalate here, positive, negative, and so on. So imagine, they're like closely packed together. So imagine that you hit this crystal lattice with a little hammer or like microscopic hammer, and that's going to shift over the crystal lattice. So you're just going to see here we have opposite charges aligned with each other. And opposite charges, they repel each other, right? So in the macro, we're going to see a break of that lattice, which in turn means that these crystal lattices are pretty brittle, which is a characteristic of these crystal lattices. So we have here that ionic compounds form crystals. And covalent bonds, in the other hand, they form molecules such as this water molecule right here. So because ionic compounds, they are so tightly together, they also have very strong interactions, right? And that really influences the melting point of the molecule. Here we have that this specific ionic compound, so table salt or sodium chloride, has a melting point of around 800 degrees Celsius. And you probably know that water, its melting point is around 0 degrees Celsius because of ice. This means that the melting point of salt is 800 times more than water, which is no surprise that salt is pretty much a solid. Meanwhile, water can exist in multiple phases. So it can exist in solid form as ice. It can exist in water or liquid. And lastly, it can exist as gas in the form of steam. So we know that, ionic bonds are pretty much solid, and covalent bonds can exist in multiple phases. Another cool property of ionic and covalent bonds is their solubility and how they dissolve. So we're gonna go back here to our example of the crystal lattice of sodium chloride. I'm gonna add a little bit of water. So as I mentioned, here's our salt crystal, here's a water molecule, and water molecule has these two partial charges, so the partial negative and the partial positive, as we discussed over here. And as soon as you add water to this crystal lattice of table salt or sodium chloride, it will dissociate in its respective charges. So here we have the chloride aligning with the positive or partial positive side of the water, and here we have the sodium aligning with the negative part of the water. So as the salt dissociate in respective charges, we're gonna see a lot of this positive and negative in the water, which also leads to another cool property, which is conductivity. So we're gonna put over here conductivity. And the more ions we see in water, the more electricity is going to be conducted around. So we have more, because we have more of these ions floating in water. For covalent bonds, it's a little bit different. So we're going to have sugar, which is a polar molecule. So here we have our sugar molecule. As I mentioned, it's a polar molecule, so it's similar to water. It's going to have partially positive and partially negative. And here you're going to dissolve in water. We're going to have some water molecules with its partially negative and partially positive side. But when we add sugar to the water, it's not going to dissociate in ions. It's still going to be a molecule. It's just going to be solvated by the water. And the water is still going to be annihilated with the positive and negative charge of the sugar. So since the sugar cannot dissociate in ions, so this makes them pretty poor electricity conductors. And so that will be like our last property. So electricity. We know that ionic compounds are pretty great at conducting electricity in water, but covalent molecules or molecules with covalent bonds are not. And those are all the properties that we want to discuss today. So we have electrons, electronegativity, that ionic compounds form crystals, which are usually solid, and covalent bonds usually exist in different phases. And ionic compounds have great conductivity in water, meanwhile covalent bonds don't conduct electricity pretty well because they don't dissociate in their respective ions. And that's all I have for y'all today.